Hi, I'm Zeng from Brooks Group and also from NIH. And thank you for letting me have this opportunity to report our group's work based on a QM method. Okay, as we know, we have 24 small molecules and also more than 300 microstates was provided. So I would like to introduce our philosophy. First, I hope my method be simple, like simple the theory, the simple and also the process. So I can make it automatically, usually just by one click. And I need it to be fast because we need to submit it in time, and also accurate because it should be useful. And less parameters, less software is just my personal preference because I think less parameters would help people to use my method simply. And less software means less communications between different software, because sometimes different software may have different physical constants. And also maybe some groups are lack of funding, so they don't have money to buy a lot of softwares. So let's start from type 1. So in front of us, there are two choices. The first one is the absolute scheme, and then the relative scheme. Here, I just choose to use absolute scheme because, as you know, there are more than 300 microstates. I don't like to do them. There are also more than 300 microstate pairs. I don't want to do it manually, and that's much too subjective. So I try to do it absolute in this absolute scheme, but I hope the SE can be as low as possible. And for the type 2, I also need to represent the quantity we need, the population, as a function of the absolute free energy in the aqueous solution. And for the type 3, we can just use the formula from type 2, and then finally you can also get the function of the macroscopic pKa in the function of the absolute free energy. And we should note here the absolute free energy for the proton in the in aqueous solution is necessary here. When we need to compute the free energy, we usually need the thermodynamic cycle, because all the implicit solvent model we are using are usually optimized to fit the solvation free energy. So we also need to calculate the free energy in the gas phase. But for here, I would like to also introduce some schemes without the thermodynamics thermodynamic cycle as a comparison. For this scheme, the direct scheme just directly use the free energy from the assembly calculation, and also a single point correction, which means I do another single point calculation in the larger basis set. And also there are 3 different schemes with thermodynamic cycle. The first one is just to optimize the structure in the gas phase and directly use the geometry in gas phase, do a single point calculation in aqueous solution. Here we use SMD implicit solvent model. And for this diabatic scheme, we also need to optimize the structure in SMD. And for this better scheme, a diabatic scheme with single point correction also need to do a larger basis set single point calculation in both SMD and gas phase. Here we just use one software, Gaussian 16, for our quantum calculation. MO62X is used with SMD MP7 model just because of our previous sample 5 log D calculation. But here I use 2 different basis sets for different types of microstate, just because for negatively charged state, we need a diffuse function to describe the electronic structure. But for the positively charged microstate, we should not use the diffuse basis function, which can give wrong result. So for type 2, we use diffuse basis function only when pH is greater than pKa microscopic pKa, between -1 and 0, -1 and neutral macro state. So we need to do this type 3 calculation first before type 2. If we want to consider the global minimum, because that would be more reasonable, then we need to generate some random configurations first, and then choose the lowest, choose the configurations with the lowest energy by using corresponding quantum method. If we want to do it better, then we need to scan all the flexible, all the bonds which is not in a ring but with high barrier. But this step is optional because we may not have enough time to do this. Okay, and for this is our submitted result. Note here, without thermodynamic cycle, we would miss one very important pK here. And also the correction, the RMSE is rather bad here. The best one is also 1.77, but the correlation coefficients are all quite good. So we may think something may be wrong here. So looks like you need a shift to make our result better. So I know that I just missed one term in this absolute free energy, and which is just 1.89 kcal/mole, but changed my result a lot. After this correction, our RMSE can be as low as 1.21 pK units. Although it's not the best one, but it's now much better. After this correction, all the RMSE are much better now, but note here the scheme with single point correction. For the direct scheme is still worse than the one without correction. And they are all the worst one. Okay, so I've corrected. They are all, most of them are in the torrents. Some of them are still maybe a little bit far from the reference line. Now let's look at the molecules we didn't do well. All of them looks like quite normal site. So we are still working on this. If we can solve this problem, our result can be much better. Okay, so the lessons from sample 6. Thermodynamic cycle is important here, especially for that SM14. Make a single point correction to direct schemes can be even worse. In here we use different basis sets for cations and anions can give quite good results. And the most important part is we need to take account of the change of the states. For future consideration, because absolute scheme is very sensitive to the absolute free energy of the proton. So we need to be careful with the free energy of the proton. Or you can just use a relative scheme, which even you get a very wrong, because it's not related to the free energy of the proton. But I would only use it only when we have a good algorithm to find the reference models for each pairs automatically, because that'll be better for people to reproduce the result. And there's also another method, just like using linear fit or just a chaining set. I think that's just another analog of the relative scheme. All right, and now think the Bauer and also Lobos and all the group member in our group, all group members. Thank you very much for your attention.
Questions?
So I noticed that a lot of the ones that you said you had trouble with were things that were weakly acidic or weakly basic. And I think this sort of comes back to the practicality of this, because to be honest, I don't care if you can calculate pKa of an animal, right? Because
Yes.
It's never going to be it's never going to be protein. It doesn't really matter. So did you find any relationship between the error and whether something was, so could you predict the strongly acidic and strongly basic compounds, and was it the weakly acidic or weakly basic that you had problems with, or was the error sort of across the board?
He's saying,
Sorry.
is the problem, were you doing well in the middle,
Yeah.
pKs that fell in the middle, so they're weakly basic or weakly acidic? Were you doing better there? Because that's where we need to do well.
Right.
Yeah. Let me. We can check here from the table.
I like your correlation. Can we look at the plot, the scatter plot?
Yes.
See there, you see pH Say 4 to 8. 4 to 8 is looking better.
Yeah, for the weekly base or the acid should be around here. They are much better.
Yeah, so in fact, the model does seem to be doing better around the weekly acidic, weekly basic species.
Yeah.
That's an excellent point. Other questions? Yes.
Was there any cases where you predicted the PK but a little extra compared to the experimental interval? Was there any case where the predicted number of predicted PKs was more than the number of experimental PKs?
So she's wondering whether some molecules had multiple ionization states and you predicted some ionization states, but not all of them.
Okay, I mean if the maybe the microstates they provided is not insufficient. I mean, that'll be the problem. If so, we need to find out all the microstates ourselves.
Did you think you had a one-to-one correspondence between the microstates that you found and the way you would have lined up the states experimentally? Like, could you match them?
Yeah, maybe. Sorry, can you repeat?
With a molecule that had different microstates, there were some experimental ones that were found and the ones that you predicted. Did they match?
I don't know, can experiment predict the microstate?
No, not the microstates, but there would have been, the several states found experimentally. I guess they would be macrostates found experimentally. Could you match them up?
Yes, I think so. Yes, I think it's easy to match if